Hey everyone, today we're going to talk about bond energy, like was discussed in the video that you took notes on. So I'm going to show you how you can use changes in bond energy to calculate a delta H for a reaction. So let's take a look. So they talked about making bonds and breaking bonds. And so we can use this concept of measuring energy from bonds that are broken and energy from bonds that are formed to come up with the overall change in heat. So this will be what we're trying to calculate, delta H for a certain reaction. And so to do that, we want to look at all of the energy from the bonds broken. So energy is required to do this. So if we add up all the energy that we need to break bonds, and then compare that to the energy that's released when new bonds are formed, if we take the difference between the energy required and the energy released of all of those, then it will tell us the change in H for the reaction. So if you look at the first example, the big picture on your sheet there, we have some hydrogen and some oxygen forming water. Now, if we look at the reactant side, these are the bonds that could be broken. Now, in this particular example, it turns out that every single one of these bonds is broken, but you really just need to track the ones that break, see how much energy comes from those, and then the bonds that are formed will show up over here on this side, on the product side, and we can track those, and if we do broken minus formed, then the difference will be the delta H. So if you look, we are going to break HH bonds. And the reason we can tell that is because we see an HH bond here, and we don't see any over here. So where we had a hydrogen-hydrogen single bond, we don't anymore, so we know that gets broken. So what we want to do is look up the energy for an HH single bond, which happens to be 436, and you can find that right on the sheet. But we got to multiply that by 2 because there are 2 HH bonds. So that gives us a total of 872. Now, the other thing that we break is an OO double bond because we have one here and we don't have one on the other side. So we look up the energy for an OO double bond. Make sure you get the double one, not the single. And that's going to be 495. Now, because there's only one of those, that works. Now, those are all the bonds, so the sum of all the bonds that are broken is 1367. So let's look at the product side now. We can see that we are forming a single bond between O and H. We didn't have that before on the other side. So if you count, we have lots of OH single bonds. In fact, we have 1, 2, 3, 4 of them. So if you look up an OH single bond on your chart, that is 463. But we need to multiply it by 4 because we have 4 of them. So when we do that, we get 1854. Now, if you combine those two together, the sum of the energy for the bonds broken minus the energies of the bonds formed, that will tell you delta H for the overall reaction, which in this case is negative 487, and that's going to be in kilojoules per mole. Now, when you get a negative number like that, that, remember, tells you that the reaction is exothermic. So that energy is being released and is available to do work. So by looking at the energy from the bonds that are broken and comparing it to the energy from the bonds that are formed, we can see how the overall energy of the reaction changes. So that's what you're going to do. Now, obviously, you want to start with a Lewis diagram of your reaction so you can see which bonds you have. Then make a list, broken and formed, and then combine those, and you will get your answer. So try that out and see how it goes. If you have questions, you can just send me a message, and I'll get back to you with some help. So take a look and see what you can do with that practice that is attached. All right, good luck.